close your eyes for a moment and imagine the whole universe, every star, every galaxy, every wisp of gas and light, compressed into something smaller than a grain of sand. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. That image, as strange as it is, sits at the center of one of the oldest and deepest questions human beings have ever asked. Not just where did everything come from, but what, if anything, came before it. Tonight, we are going to sit with that question together. We are not going to answer it. No one can, not yet. We are simply going to look at it from every angle we know. The way you might turn a smooth stone over in your hand in the dark, feeling its shape without quite being able to see it. Start as far back as your mind will go. Picture the universe as it is right now. Hundreds of billions of galaxies, each one holding hundreds of billions of stars. Light traveling in every direction at once. Planets spinning in slow, patient orbits. Moons casting pale shadows across frozen plains. All of it moving, all of it expanding, all of it spreading outward from a single point in time that we call the Big Bang. The Big Bang happened roughly 13.8 billion years ago. That number is large enough that it loses its meaning almost immediately. 13.8 billion years. The oldest light we can detect left its source when the universe was less than 400,000 years old. Before that, the universe was too hot and too dense for light to travel freely at all. It was opaque, like a wall of glowing fog, and nothing could pass through it. So even our best telescopes, the most powerful instruments we have ever built, cannot see past that wall. They can see up to it. They can study the faint glow it left behind, a soft hum of ancient radiation that fills the whole sky, but they cannot see through it. And what came before it, if anything did, remains hidden. That is the edge of the observable universe in time, not in space, but in time. And standing at that edge and asking what came before it is one of the most honest things a human mind can do. Here is where the question becomes genuinely strange. When we ask what came before the Big Bang, we are not just asking about a moment we cannot see. We may be asking about a time before time itself existed. Because according to our best current understanding, time as we experience it, as a sequence of moments moving in one direction, may have begun at the Big Bang, or very near it. The mathematics that describe the universe start to break down as you approach that first instant. They do not simply run out of answers. They stop making sense. Some researchers believe that asking what came before the Big Bang is like asking what is south of the South Pole. The question sounds reasonable, but the structure of the thing you are asking about may make the question impossible to answer, not because we lack information, but because the concept of before may not apply. Others disagree. Some physicists think time did not begin at the Big Bang. They think the bang was not a beginning at all, but a transition, a moment of enormous change in something that already existed. Under those ideas, there was a before. It just looked nothing like what we know. There are several serious theories built around this possibility. Some imagine a universe that collapsed and then bounced back outward, like a breath drawn in and then released. Others imagine vast, thin sheets of something floating in a higher dimensional space that collided and sparked our universe into being. Still, others suggest our universe grew like a bubble from a larger, older structure that has no beginning we could ever trace. None of these ideas has been proven. None has been ruled out. They are honest attempts by careful thinkers to reach past the edge of what we can see. And so tonight, as you settle in and let your body grow heavy and still, that is the question we will carry together. Not with urgency, not with fear, just with quiet, open curiosity. What was there, if anything, before the first moment, before the light, before the heat, before the first particle found its shape? Was there a silence before the silence? A darkness before the dark? We do not know. And that, in its own way, is a beautiful place to begin. Before we can wonder about what came before the Big Bang, it helps to understand what the Big Bang actually was. Not the version from a science class you half remember. The real thing, as best as we understand it today. Because the truth is stranger and quieter than most people expect. The Big Bang was not an explosion. That word carries the wrong picture. When you hear explosion, you imagine fire and noise, and something flying outward through empty space. But the Big Bang was not like that at all. There was no empty space waiting to receive it. There was no surrounding darkness for it to expand into. Space itself was part of what began. The universe did not appear inside something else. It was the something else. What the Big Bang describes is the earliest moment we can trace with our current understanding of physics. About 13.8 billion years ago, everything we can observe, every star, every galaxy, every atom in your body was compressed into a state of almost unimaginable heat and density. Not a single point floating in a void, just a state, a condition, smaller than anything we have words for, and hotter than any temperature we can test in a laboratory today. To give that number some weight, 13.8 billion years is roughly 3 times the age of our own planet. Our sun has not even existed for half that time. The oldest stars we can see are ancient beyond easy thought, and yet they came long after that first moment. The universe was already hundreds of millions of years old before the first stars switched on. From that first hot, dense state, the universe expanded. It cooled as it grew, the way a gas cools when it spreads out. Within the first few minutes, the basic building blocks of matter began to form. Protons and neutrons, the tiny cores of atoms, came together in the heat. Hydrogen and helium, the 2 lightest elements, were born in those early minutes. Everything heavier than that would have to wait for stars. For a long time after, the universe was a thick, hot fog. Light could not travel freely through it. The fog was too dense. Then, about 380,000 years after the beginning, the universe cooled enough for electrons to settle around atomic nuclei. The fog cleared. Light moved freely for the first time. That ancient light is still traveling today. We call it the cosmic microwave background, a faint glow that fills the entire sky, a kind of afterglow from that first clearing. It is one of the most important things we have ever detected. But here is where the story gets complicated. When we say the Big Bang was the beginning, we have to be careful about what that means. Our best tools in physics, the equations we use to describe gravity, space, and time, break down at the very first instant. They stop giving us useful answers. The closer we zoom in toward that first moment, the less reliable our math becomes. There is a boundary very close to the beginning, past which our current understanding simply does not reach. That boundary is called the Planck epoch, a window of time so short it makes a single second seem like an eternity. In that window, the forces of nature as we know them were likely merged into one. The rules were different, and we do not yet have a theory that can describe what was happening there with any confidence. Some researchers think the Big Bang was a true beginning. That time itself started there, and asking what came before is like asking what is south of the South Pole. The question may not have an answer because the framework that makes before meaningful did not yet exist. Others believe the Big Bang was not a beginning at all, but a transition. Something came before it. Something caused it or gave rise to it. These are not fringe ideas. They come from serious work in theoretical physics, but they remain unproven. So the Big Bang is, in the most honest terms, the earliest moment we can describe with reasonable confidence. It is not the moment of creation in any final sense. It is the edge of our knowledge. Beyond it, the picture goes dark. Not because nothing was there, but because we have not yet found a way to see. That edge is what this whole episode circles around. Not the bang itself, but the silence before it. The question of whether before even has meaning. The possibility that our universe has a history we may never fully read. For now, though, let the image settle. A universe beginning in heat and light, expanding slowly into the dark, cooling as it goes. And somewhere behind it, a question that has no answer yet. Imagine standing at the edge of a vast, dark ocean. You can see a long way out. The water stretches to the horizon, and beyond that horizon, you simply cannot see. Not because there is nothing there, but because the light from that distance has not had time to reach you yet. The universe works in a similar way. There is a boundary to how far we can observe. Scientists call it the observable universe, the sphere of space whose light has had enough time, across nearly 14 billion years, to travel to us. Everything inside that sphere, we can study. Everything outside it remains, for now, beyond our reach, and somewhere very close to the edge of that sphere, our ability to trace the story of the universe begins to blur. The further back in time we look, the closer together everything was. The galaxies we see today were once much nearer to one another. Before the galaxies, there was only hot, glowing gas. Before the gas, there was a dense, bright plasma, a kind of thick, charged soup of particles so tightly packed that light could not move freely through it. And before even that, the universe was so small and so hot that our best physical models begin to strain under the pressure of the question. There is a moment in the very early universe that physicists call the Planck epoch. It is the earliest slice of time our current equations can even attempt to describe. It lasted only about 10 to the power of minus 43 seconds. A number so small it has no meaning in everyday life. A fraction of a fraction of a fraction of a single second. During this moment, the universe was smaller than an atom. The temperatures and densities involved were so extreme that the four known forces of nature, gravity, electromagnetism, and the two nuclear forces, may have all been a single unified force. After that moment, things began to separate and cool. The forces split apart. Particles formed. The universe expanded, and the story we know began to take shape. But here is where the edge appears. The Planck epoch is not just a very early moment. It is the wall. It is the place where our mathematics breaks down. General relativity, the theory that describes how gravity shapes space and time, and quantum mechanics, the theory that describes how the very smallest things behave, do not agree with each other when you push them to those extremes. They give different answers. They point in different directions. And until we have a theory that unifies them, we cannot see past that wall. Some researchers believe that wall is not the true beginning. They think it is simply the edge of what our current tools can reach. One idea is that a more complete theory of quantum gravity, a theory we do not yet have, would let us push past the Planck epoch and see what came before. What that would reveal, no one can say with confidence. Others hold a different view. They suggest the Planck epoch is not just a practical limit, but a fundamental one. That asking what came before it is like asking what is north of the North Pole. The question sounds reasonable, but the structure of space and time may simply not allow for an answer in the way we expect. This second view connects to something called the Hartle-Hawking no-boundary proposal. Two physicists suggested that time itself may have had no sharp starting edge. Instead of a hard beginning, time may have curved smoothly into existence the way the surface of a sphere curves. No corner, no edge, no single point where it all began. Under this idea, asking what came before the Big Bang is not a question with a hidden answer. It is a question that may not map onto reality at all. But that proposal is not settled either. Other researchers find it unsatisfying. They feel it sidesteps the question rather than answering it. The debate between these views is still very much alive. What we can say with some confidence is this: the universe we observe had a beginning of some kind. The evidence for that is strong. The cosmic microwave background, the faint glow of ancient light that still fills the sky in every direction, points clearly to a hot, dense, early state. The expansion of galaxies points backward to a single origin. The abundance of light elements like hydrogen and helium matches what the early universe should have produced. The beginning happened. What we cannot yet agree on is whether that beginning was truly the first moment of everything, or whether it was simply the edge of what we can see. There is something quietly strange about the word before. We use it every day without thinking, before breakfast, before sleep, before the sun came up this morning. The word feels simple, almost invisible. But when physicists try to apply it to the Big Bang, something unexpected happens. The word starts to lose its grip. It starts to slip. To understand why, it helps to think about what time actually is. Not time as we feel it, the slow drift of an evening, the way an hour can feel like a minute when you're at rest. But time as physics describes it. In the picture that Einstein gave us, time is not a backdrop. It is not a stage that the universe performs on. Time is woven into the fabric of space itself. The two are bound together, inseparable, like the length and width of a single piece of cloth. Physicists call this fabric spacetime, and it is the very material from which the universe is made. Here is where things get quietly strange. If spacetime is a thing, a physical thing with structure and shape, then it had to come from somewhere. And most of our best models suggest that spacetime itself began at the Big Bang. Not just matter, not just energy, but time. If that is true, then asking what came before the Big Bang may be like asking what is north of the North Pole. The question sounds reasonable. It sounds like it should have an answer. But the direction you are asking about simply does not exist beyond that point. There is no north past the pole. There may be no before past the beginning of time. This idea was developed carefully by two physicists, James Hartle and Stephen Hawking, in the 1980s. Their proposal is sometimes called the no-boundary proposal. The idea is that time, near the very beginning of the universe, behaved more like a dimension of space than like the time we experience now. In that condition, the question of what came before loses its meaning. The beginning is smooth and closed, like the surface of a sphere. A sphere has no edge. It has no starting point. You can travel across it in any direction and never reach a boundary. It is a beautiful idea, but it is also deeply strange, and not everyone finds it satisfying. Some researchers push back and say the no-boundary proposal sidesteps the question rather than answering it. If time emerged from something more like space, they ask, what was that space-like condition doing before it became time? What set the rules that allowed it to exist at all? The proposal may describe the shape of the beginning without explaining why there was a beginning in the first place. This is where another set of ideas enters the picture. In a branch of physics called loop quantum cosmology, researchers work with a different picture of space-time. Instead of treating it as a smooth, continuous fabric, they propose that space-time has a kind of grain to it, a smallest possible unit, the way matter has atoms. In this picture, you cannot divide space or time forever. At some point, you reach the smallest possible piece. If that is true, then the Big Bang was not a true beginning. It was a transition, a moment when an earlier contracting universe reached its smallest possible size. condensed outward into expansion. Time in this picture did not start. It continued. It was always there, stretching back through a previous universe we can no longer see. These two ideas, the no-boundary proposal and the loop quantum bounce, point in very different directions. One suggests time had a beginning, and the question of before is simply unanswerable. The other suggests time had no beginning, and there was always something, even if we cannot reach it with our instruments. Both ideas are built on solid mathematics. Both are taken seriously by working physicists, and neither one has been confirmed by observation. What we can say is this: the building blocks of our universe, the matter, the energy, the very fabric of space-time, all trace back to conditions we cannot fully describe. Our equations begin to break down at the very first moments. The tools we use to understand the universe were built inside the universe, and there is a real question about whether those tools can ever reach past the boundary of their own origin. Time may have started, or it may have always been, or the question itself may need to be rewritten before it can be answered. For now, the building blocks of existence sit quietly at the edge of what we can know. And that edge is a strange and peaceful place to rest your thoughts. There is a kind of silence that is hard to imagine. Not the silence of a quiet room, or a still forest, or a night without wind. This is a silence before sound was even possible, before air, before matter, before anything that could carry a vibration from one place to another. Whatever existed before the Big Bang, if anything existed at all, it existed in a state so unlike our own that the word silence barely fits, and yet it is the closest word we have. When physicists try to think about what came before the Big Bang, they keep running into the same invisible forces, the same deep pulls and pressures that shape everything we can see today. Gravity, energy, the strange tension built into space itself. These forces did not appear from nowhere when the universe began. Or at least, that is one possibility. Another possibility is that they did, that they were born at the very moment of the bang, with no history behind them at all. The question of which is true remains open. Gravity is the most familiar of these forces. It pulls mass toward mass. It bends space around heavy objects. We feel it every moment of our lives. But gravity at the very beginning of the universe was something far stranger than the gentle pull that keeps your feet on the ground. In the first fractions of a second after the Big Bang, gravity was tangled up with the other fundamental forces. The forces that hold atoms together, that push particles apart, that govern how light behaves. Some researchers think all four fundamental forces were once a single unified force. One thing, not four. Then, as the universe cooled and expanded, they separated. Like steam cooling into water, then water freezing into ice. The same substance, but changed. What that unified force looked like before the bang, or whether it existed at all, is one of the deepest unsolved problems in physics. We do not have a theory that fully describes gravity at the smallest scales. The equations that describe the very large, like galaxies and black holes, do not connect cleanly with the equations that describe the very small, like atoms and particles. This gap in our understanding is sometimes called the problem of quantum gravity, and it sits right at the heart of the question of what came before. Some researchers think that before the Big Bang, space itself was filled with a kind of energy, a pressure built into the vacuum, the empty space between things. This is sometimes called vacuum energy, or the energy of the quantum field. It is not nothing. Even empty space, according to quantum theory, hums with a faint activity. Particles flicker in and out of existence. Energy rises and falls in tiny waves. One idea is that this restless energy was present before the bang, and that it was the engine that drove the explosion into being. A kind of pressure that had been building, waiting, until it finally released. But another idea says that is the wrong picture entirely. Some models suggest there was no before in any meaningful sense. That time itself was born at the bang, and asking what forces were at work before that moment is like asking what is south of the South Pole. The question sounds reasonable, but it may not have an answer, because the direction you are asking about simply does not exist. Still, the forces we observe today carry clues. The way the universe expanded so evenly in all directions suggests something was smoothing it out, pressing it flat, ironing away any wrinkles. That smoothing process is called inflation, a brief, extraordinary burst of expansion in the universe's first moments. What drove inflation is still debated. Some think it was a special kind of energy field that filled early space. Others think inflation points towards something that came before, a pre-existing state that set the conditions for the bang to happen the way it did. The silence before the first sound, then, was not truly empty. Or at least, it may not have been. It may have been full of forces we do not yet understand, pressures and fields and energies that had no matter to act upon, no light to carry them, no space in the way we know space. Just the deep, invisible architecture of physics, waiting. We cannot hear that silence. We cannot reach back to it. Our instruments can only see so far, and the moment of the bang sits at the very edge of what is visible. What pressed against the other side of that edge? What forces hummed in whatever came before? That remains, for now, a question without an answer. And perhaps that is enough for tonight. To know the question is there, to feel the weight of it gently as you rest. There is a moment very late at night when the house goes quiet and the numbers stop making sense. You try to picture a billion of something, a billion grains of sand, a billion seconds. The mind reaches out and then quietly gives up. That giving up feeling is worth holding on to, because the mathematics behind what came before the Big Bang lives in a place so far beyond ordinary scale that even the physicists who write the equations admit the numbers feel more like poetry than measurement. Start with something you can hold. A single grain of salt. That grain is roughly 1 millimeter across. Now consider that the observable universe, everything we can possibly see with any telescope, every galaxy, every star, every wisp of gas, stretches about 93 billion light years from one edge to the other. A light year is the distance light travels in a full year, moving at 186,000 miles every single second. The grain of salt and that number don't belong in the same thought. And yet, physicists ask us to go further. They They ask us to think about what existed before all of that. The theories that try to answer that question are not written in plain language. They are written in mathematics so dense that only a small number of people on Earth can read them fluently. But the shapes those equations describe are something anyone can feel. They describe a universe that may have been, at the very first instant, smaller than that grain of salt. Smaller, in fact, than the smallest thing you could ever see under any microscope. The entire seed of everything we know may have fit inside a space far tinier than a single atom. An atom is already almost impossibly small. If you blew up an apple to the size of the Earth, the atoms inside that apple would be roughly the size of the original apple. That's how small an atom is. And the theories suggest the early universe was smaller still. Not just a little smaller, incomparably smaller. The mathematics points to a starting point so compressed that our normal rulers simply stop working. This is where the equations become something close to humbling. In the first fraction of a second after the Big Bang, temperatures reached numbers that have no comparison in daily life. One estimate puts the temperature at the very earliest calculable moment. A sliver of time called the Planck time, which is about 10 million trillion 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 times shorter than 1 second. At around 100 million 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 degrees. Writing that out doesn't help. The sun's core, by comparison, sits at about 27 million degrees Fahrenheit. The early universe was not just hotter. It was unimaginably, categorically hotter in a way that makes the sun feel like a cool breeze. And here is where the open question quietly enters the room. Those equations, as precise as they are, break down right at that boundary. The Planck time is not just a very small number. It is the smallest unit of time that current physics can meaningfully describe. Ask what happened before it, and the math returns something called a singularity, a point where the numbers go to infinity and the equations stop giving useful answers. Some physicists treat this as a wall. Others treat it as a door. One idea, rooted in a theory called loop quantum cosmology, suggests the equations break down not because nothing was there, but because our current tools aren't sharp enough to see it. In this view, the universe before the bang was real and physical, just described by a kind of mathematics we haven't fully built yet. The singularity in this picture is a gap in our knowledge rather than a gap in reality. A competing idea tied to the Hartle-Hawking no-boundary proposal suggests the equations break down because time itself didn't exist in the same way before the bang. In this picture, asking what came before is like asking what is south of the South Pole. The question sounds sensible, but the geometry of the answer makes the question dissolve. There is no south of south. There may be no before of before. Both ideas are written in the same dense mathematical language. Both are taken seriously by serious people. Neither has been confirmed. The equations point in different directions, and the universe has not yet told us which path leads somewhere real. So the numbers sit there, enormous and microscopic at once. A universe born smaller than an atom, a temperature beyond any comparison, a moment of time so brief it has no name in ordinary speech. And at the center of all those numbers, a question that the math itself cannot yet answer. What, if anything, was there before the equations began? Imagine standing at the edge of a great wave. Not a wave on any ocean you have known, but something far older and far larger. A wave that is the universe itself, rising and falling, expanding and contracting, breathing in and out across unimaginable stretches of time. This is the picture that one group of ideas places before you. It is called the bouncing universe. The core thought is simple, even if the mathematics behind it is not. Our universe did not begin from nothing. Instead, it collapsed from something that came before, squeezed down to a point of almost unthinkable density, and then bounced back outward. The Big Bang in this picture was not a beginning. It was a rebound. Think of a ball dropped from a great height. It falls, it strikes the ground, and then it rises again. The bouncing universe asks whether something like that could be true of the cosmos itself, whether the universe we live in is one upswing in a long series of falls and rises that may have been going on forever. One version of this idea comes from a field of study called loop quantum cosmology. This approach tries to combine two great theories of physics that have never fully agreed with each other. General relativity, which describes gravity and the large-scale shape of space, and quantum mechanics, which describes the behavior of the very small. When physicists use loop quantum cosmology to trace the universe backward in time, something unexpected happens. The equations do not break down at the Big Bang. They keep going. They suggest that before the expansion, there was a contraction, and that the extreme density of that collapse did not reach an infinite point, but instead reached a very high but finite limit, then reversed. In this picture, if you could somehow float above the moment of the Big Bang and look back through it, you would not see a wall of nothing. You would see another universe contracting toward you like a dark mirror image of our own. Picture that. A vast space growing smaller and smaller, its stars burning out one by one, its galaxies pulling together, the light growing redder and dimmer as everything draws inward. The colors would shift. What was once the warm gold of a living star would cool to deep amber, then to red, then to a faint infrared glow that no human eye could follow. The geometry of space itself would be curving inward, folding, tightening, and then, at the moment of greatest compression, something would push back. That push is what loop quantum cosmology calls the quantum bounce. The idea is that space, at its smallest possible scale, has a kind of granularity, a texture, like a fabric woven from loops too small to ever see. When the universe is squeezed down to the scale of those loops, the fabric resists. It cannot be compressed further. And so it expands again. What we call the Big Bang may have been that moment of resistance. It is a beautiful image, but it is not the only one, and it is not without its difficulties. Some physicists point out that a truly bouncing universe faces a deep problem involving entropy. Entropy is a measure of disorder. Most physical processes tend to move from order toward disorder over time. A bouncing universe would need to somehow reset its entropy with each cycle. Otherwise, each successive universe would be more disordered than the last, and the chain could not go on forever. Some researchers think there are ways around this. Others are not convinced. There There is also the question of what the bounce actually looked like from the inside. The mathematics suggests a transition, but the physics of that transition is not fully understood. Quantum gravity, the theory that would properly describe what happens at those extreme scales, is still incomplete. The bounce is a prediction of certain equations, but those equations themselves are still being tested and debated. So the picture remains open. The universe as a great wave, rising and falling. The Big Bang as a rebound rather than a true beginning. The cosmos before ours as a contracting mirror of everything we see tonight. Its light fading, its space folding, until the smallest possible scale of reality pushed back and sent everything outward again. Whether that picture is true, whether it can ever be tested, whether the mathematics will hold up as physicists learn more, none of that is settled. The bouncing universe is a possibility, carefully constructed, genuinely considered, and still very much a question. For now, let the image rest quietly in your mind. A universe breathing in, a universe breathing out, and somewhere in the middle of that breath, everything we have ever known. There is a question that sits just beneath the surface of everything we have talked about so far. It is quiet, but it does not go away. If the universe began in an enormous burst of heat and light and energy, what was there before that burst? And what if the answer is another universe, very much like our own, that came before? This is not a fringe idea. Some physicists take it seriously. The general shape of the theory goes like this. Our universe did not begin from nothing. It began from the collapse of a universe that existed before it. That earlier universe grew, expanded, aged, and then fell back in on itself under its own gravity. And at the moment of that collapse, something extraordinary happened. Instead of simply ending, that universe bounced. It rebounded outward with tremendous force. And that rebound is what we call the Big Bang. The idea has a name. It is called the Big Bounce, and it comes in several forms, depending on which physicist you ask. One version comes from a field called loop quantum cosmology. Loop quantum cosmology is a way of thinking about gravity at the very smallest scales, smaller than anything we can measure directly. In ordinary physics, when you try to squeeze matter and energy into an infinitely small point, the math breaks down. You get numbers that don't make sense. But loop quantum cosmology suggests that space itself is not perfectly smooth. It has a kind of grain to it, like a fabric woven from tiny loops of geometry. And when matter gets compressed down to that scale, something resists. A pressure builds, and instead of collapsing to a point, the universe bounces back outward. In this picture, the Big Bang was not a beginning. It was a turning point. The universe before ours reached its smallest possible size, hit that quantum floor, and expanded outward again. Our universe is the result of that expansion. And one day, if the math holds, our universe may do the same thing. It may slow, contract, compress, and eventually give rise to a universe after ours. That is a strange and quietly beautiful idea. It suggests that time does not have a beginning. It just cycles. Each universe gives birth to the next, the way one wave rolls into another on a long, slow shore. But not everyone agrees that this is what happens. Some physicists point out that the bounce may not be as clean as it sounds. When a universe collapses, it does not collapse evenly. Different regions fall inward at different speeds. The result would be something chaotic and irregular, not the smooth, nearly uniform universe we actually observe around us. Our universe looks remarkably even in all directions, at least at the largest scales. A messy bounce might not produce that evenness. Others raise a different concern. Even if a bounce happened, the information from the universe before ours might not survive. The conditions at the moment of maximum compression would be so extreme that almost nothing from the previous universe could pass through intact. So even if there was a universe before ours, we might never be able to see its fingerprints in our own. And yet some researchers are not ready to give up on that possibility. There are physicists who believe that certain patterns in the oldest light we can observe, the faint glow left over from the early moments of our universe, might carry traces of what came before. Not clear images, not messages, just subtle hints. Slight variations in temperature or density that could, in theory, reflect the shape of a universe that existed before our own. The search for those hints is ongoing. The evidence is not yet strong enough to draw firm conclusions. Some researchers think they have spotted something. Others look at the same data and see noise. The question remains open. What is striking about the Big Bounce idea is how much it changes the way you think about the word beginning. If the universe bounces, then our Big Bang was not the first event in time. It was just the most recent one we can trace. Time might stretch back through bounce after bounce, universe after universe, further than any telescope could ever reach. Or it might not. The bounce might be a beautiful idea that the universe simply does not use. We do not yet have the tools to know for certain. For now, the question rests there, deep beneath the surface of everything we can see. Before our universe, was there another? Did it collapse? And did we rise from that collapse? The math allows it. The observations do not yet confirm it, and the silence between those two facts is where the mystery lives. There is a rhythm to almost everything. The moon pulls the ocean up and lets it fall. Stars are born from clouds of gas, burn for millions of years, and collapse back into the dark. Planets cool, crack, and sometimes warm again. Even the largest structures in the universe seem to breathe in slow, enormous cycles that we are only beginning to trace. Some researchers wonder whether the universe itself follows a rhythm like this. Not just one bang and one expansion, but something that pulses, something that repeats. And at the very bottom of that idea, smaller than any cycle we can easily picture, there may be something stranger still, a kind of restlessness built into the fabric of space itself. Physicists sometimes call it quantum foam. The idea comes from a deep corner of physics, where the very small and the very large meet and don't quite agree. At the scale of atoms and smaller, the universe does not sit still. Energy flickers. Particles appear and vanish in tiny fractions of a second. Space itself, at the smallest scales we can imagine, may not be smooth at all. One possibility is that it bubbles and churns constantly, like the surface of water just before it boils. This restlessness is not a flaw in the universe. Some physicists think it may be one of its most basic features. The physicist John Wheeler first used the phrase quantum foam to describe this idea. He imagined that if you could zoom in far enough, past atoms, past protons, past anything we've ever measured directly, space would stop looking like a flat, quiet surface. It would look more like something alive, twisting, foaming, constantly shifting at a scale so small it makes an atom look enormous by comparison. Now here is where the question of before the Big Bang quietly enters the picture. If space has this restless, foaming quality at its smallest scale, then perhaps the Big Bang was not a beginning in the way we usually imagine. Perhaps it was more like a bubble. One particular fluctuation in the quantum foam that grew and kept growing until it became everything we see. The entire observable universe on this view might have started as a tiny tremor in something that was already there, something that had no clear beginning of its own. This is one of the ideas that sits inside loop quantum cosmology, a framework that tries to combine the physics of the very small with the physics of the very large. In this view, the Big Bang was not a true starting point. It was a bounce. The universe before ours collapsed inward, reached a point of extreme density, and then the quantum effects of space itself pushed back. The collapse reversed. A new expansion began. What we call the Big Bang was the moment of that reversal. But other physicists are not convinced this picture holds together. The mathematics of loop quantum cosmology is still being developed. Some researchers point out that we have no direct observational evidence that a bounce actually happened. The signals from that moment, if they exist at all, would be buried so deep in the noise of the early universe that we may never cleanly separate them from everything else. There is also a competing idea that doesn't require a bounce at all. In the Hartle-Hawking no-boundary proposal, which was explored in earlier sections, time itself may have had no sharp edge. The universe didn't emerge from something else. It simply came into being the way a sphere has no edge, no point where it starts. On this view, asking what the quantum foam was doing before the Big Bang may be like asking what is south of the South Pole. The question sounds reasonable, but the geometry doesn't allow an answer. So the two ideas sit side by side, unresolved. One says the foam was there first, and the bang was just one of its rhythms. The other says there was no before at all, and the foam, if it exists, is part of the universe, not something older than it. What both ideas share is a sense of something restless at the base of things, something that doesn't fully stop, even in the deepest silence of space, even in the emptiest region between galaxies. The quantum world may be flickering. Tiny fluctuations, too small to see, too brief to measure directly, humming away beneath everything. Whether that restlessness is the source of universes or simply a feature of the one we live in remains an open question. For now, let that quiet hum be the last thing you think about. The universe still flickering at its edges while you rest. Some ideas in physics sound simple on the surface. Then you sit with them a little longer, and they open into something much stranger. One of those ideas is this: the universe may have been born from nothing at all, not from a previous universe, not from a collapsing cycle or a bouncing quantum field, from nothing, from a state so empty, so utterly without content, that the word empty barely fits. And yet, some researchers think that kind of nothing is not as stable as it sounds. They think nothing, under the right conditions, might not be able to stay that way. This idea has a name in physics. It is sometimes called quantum tunneling from nothing, or more formally, vacuum genesis. The word vacuum here doesn't mean a clean floor. It means a state with no matter, no energy, no space, and no time. A true void. And the question some physicists have asked is whether even that void might be unstable. Whether something like a universe could flicker into existence from it. The way a bubble forms in still water for no obvious reason. The physicist Alexander Vilenkin explored this idea seriously in the early 1980s. He proposed that a very small, closed universe might be able to tunnel into existence from a state of absolute nothingness, not from a previous state of something, from the absence of anything. In his picture, the laws of quantum mechanics, the rules that govern the very small, allow for events that have no cause in the usual sense. A particle can appear, a universe perhaps can too. This is a hard idea to hold in the mind. We are used to asking what caused this and expecting an answer that points to something earlier. But quantum mechanics sometimes refuses that kind of answer. At the smallest scales, events can happen without a prior cause in the way we normally understand the word. Vilenkin's proposal leans into that strangeness and asks whether the universe itself might be the largest example of it. Not everyone finds this satisfying. Some physicists point out that nothing in Vilenkin's model still requires the laws of quantum mechanics to exist. And if those laws exist, is that really nothing? This is a fair challenge. It suggests that even the most radical version of born from nothing may be smuggling something in through the back door, a pre-existing set of rules, a mathematical structure, a framework within which the tunneling can occur. Whether that counts as something or not is a question that doesn't have a clean answer. The Hartle-Hawking no-boundary proposal, which came up in earlier sections, offers a different but related picture. In that model, the universe doesn't tunnel from nothing so much as it simply has no edge in time. Time itself rounds off smoothly near the beginning, the way the surface of a sphere has no edge. There is no moment of creation because there is no boundary where creation would have to happen. The universe just is, in a way that makes the question of what came before it quietly dissolve. These two ideas sit near each other, but they are not the same. Vilenkin imagines a universe appearing from a true void. Hartle and Hawking imagine a universe that has no beginning in the first place. Both are trying to answer the same deep question. Both leave something unexplained, and both require a kind of mathematics that has not yet been fully tested against observation. What's striking is how these ideas share a common neighbor: the concept of the quantum vacuum. In modern physics, even empty space is not truly empty. It hums with what physicists call vacuum energy, a kind of restless, fluctuating potential that fills space even when nothing else is there. Particles flicker in and out of existence constantly at scales too small to see. Some researchers wonder whether the Big Bang itself might be understood as one of those fluctuations, just an extraordinarily large one. That idea has its own problems. A fluctuation in the quantum vacuum still requires a vacuum to fluctuate in, and that vacuum exists within space and time. So again, the question slides back. Where did the vacuum come from? Where did space and time come from? The answer keeps retreating just past the edge of what the theory can reach. There is something quietly beautiful about that. Every time physics seems to close in on the beginning steps back a little further. Not because the universe is hiding, but because the tools we have were built inside the universe to describe the universe, and they may simply not reach all the way to the question of how it started. The question stays open. The nothing remains mysterious. There is a thought that tends to arrive quietly, just as the mind begins to slow down for the night. It is the thought that our universe, vast as it is, might not be alone. That somewhere beyond what we can see or measure, other universes may exist. And some researchers go further still. They wonder whether some of those other universes came before ours, not beside it in space, but before it in time, or in whatever stood in for time before time began. This is one of the more extreme ideas in modern cosmology, and it is worth sitting with because it changes the shape of the question entirely. If our universe is one of many, then the Big Bang was not necessarily the beginning of everything. It may have been the beginning of this particular everything. A local start. One flame lit from a fire that was already burning. The question of what came before becomes, in this framing, a question about the larger structure that contains us. And that structure, if it exists, is something we have no direct way to see. The idea of a multiverse takes several different forms, and they do not all agree with each other. One version comes from the theory of eternal inflation. In this picture, the rapid expansion that may have driven the early universe did not stop everywhere at once. It stopped here in our region, and the universe we know was born from that stopping. But elsewhere, the expansion continued. And in those other regions, other universes formed. Each one a separate bubble, cooling and settling into its own version of physics. Some of those bubbles may have formed long before ours. They would be older universes with more time behind them than we can imagine. What is extreme about this idea is the scale it implies. Not just one universe before ours, but perhaps an endless number. Each one born from the same churning, expanding background. Each one sealed off from the others by the very speed of that expansion. We could never reach them. We could never signal them. They exist, if they exist at all, in a kind of permanent silence, just beyond the edge of what is knowable. Another version of the many worlds idea comes from a different direction. Some interpretations of quantum mechanics suggest that every possible outcome of every event actually occurs, branching off into a separate world each time. In this picture, the universe before our Big Bang might not be a separate bubble drifting in an inflating void. It might be a branch, a path taken in a vast network of possible histories. Our universe would then be one branch among an uncountable number, each one equally real, each one unaware of the others. These two ideas, the bubble multiverse and the branching quantum multiverse, are not the same thing. They come from different theories and make different predictions. What they share is the suggestion that our universe is not the whole story, that the word before might point not to emptiness, but to an older, larger structure we have no tools to examine. The most extreme version of this thinking may be the one that asks whether the laws of physics themselves vary from universe to universe. In our universe, certain numbers, certain constants, are tuned in ways that allow stars to form, atoms to hold together, and life to exist. Some researchers wonder whether those numbers are fixed, or whether they are simply the values that happen to settle here. The way a coin lands on heads in one flip and tails in another. If other universes exist, they may run on entirely different rules. They may have no stars, no atoms, no stable matter at all. They would be extreme in a way that makes our universe look almost impossibly gentle by comparison. None of this is settled. The multiverse, in any of its forms, remains a hypothesis. It is a mathematical possibility that emerges from certain theories, but it has not been confirmed by observation. Some physicists find it compelling. Others argue that a theory which cannot be tested is not really a scientific theory at all. The debate is ongoing and honest and unresolved. What stays with you, though, is the image. A vast and ancient structure, older than our universe, filled with worlds that burned and cooled and perhaps ended long before our own Big Bang ever sparked. Worlds that never knew stars like ours. Worlds that ran on different rules, or no rules we would recognize. And somewhere in that structure, one small region paused its expansion, and something like our universe began. We do not know if any of that is true. We may never know. But the question itself is extraordinary, and it is yours to hold gently as the night deepens around you. There is a quiet detail hiding inside the universe. It is easy to miss. You have to look very carefully, and even then, you are not quite sure what you are seeing. When scientists study the oldest light in the universe, a faint glow left over from the early cosmos, called the cosmic microwave background, they notice something strange. That ancient light is almost perfectly smooth, almost perfectly even. No matter which direction you look, the temperature of that glow is nearly identical. The differences are tiny, smaller than a fraction of a degree. That smoothness is a mystery all by itself. Think about it this way. Imagine two rooms on opposite sides of a very large building. They have never been connected. No hallway, no window, no shared wall. And yet somehow, both rooms are exactly the same temperature. That would be strange. You would want to know why. The universe has this same problem. Regions of the sky that appear to have no connection to each other. Regions so far apart that light could never have traveled between them in the time since the Big Bang. Somehow share the same temperature, the same smoothness, the same quiet evenness. This puzzle has a name. Scientists call it the horizon problem. And for a long time, it had no good answer. Then came a theory called inflation. Inflation is the idea that the very early universe went through a period of extraordinarily fast expansion. Not the ordinary slow stretching that the universe still does today. Something far more sudden, in a tiny fraction of a second. A sliver of time so small it has no name in everyday language. The universe may have grown from something smaller than an atom to something larger than a galaxy. If that happened, then those distant, seemingly unconnected regions of the sky were once neighbors. They were once close enough to share the same temperature, the same smoothness. Then, inflation stretched them apart so quickly that they lost contact. What we see today is the memory of that ancient closeness. Inflation, if it is real, would explain the smoothness beautifully. But it raises a quieter, deeper question. What caused inflation to begin? And what was happening just before it started? Here is where the details become very small and very strange. Some researchers think inflation was driven by a kind of energy field, something they call the inflaton field. This field, the idea goes, held the early universe in a state of enormous tension, like a spring wound too tight. When it finally released, that energy drove the universe outward at astonishing speed. Then the field settled, inflation ended, and the universe began its slower, calmer expansion. But the inflaton field is still a hypothesis. No one has detected it directly. No instrument has ever measured it. It is inferred from the patterns we see, not from something we have touched or weighed. And different versions of inflation predict slightly different patterns in the ancient light. Researchers are still working to tell those versions apart. There is another detail worth sitting with. Inflation does not just smooth things out. It also stretches tiny quantum fluctuations, incredibly small ripples in the fabric of space, to enormous sizes. Those stretched ripples became the seeds of everything. Galaxies, clusters of galaxies, the great filaments and voids of the cosmic web. All of it may trace back to fluctuations smaller than anything you could see, stretched by inflation into the structure of the universe we live in. That is a remarkable thought. The largest things we know may have grown from the smallest possible disturbances. And yet, inflation does not tell us what came before it. It describes a process. It does not describe an origin. Some models suggest inflation could have emerged from a pre-existing quantum state, a kind of restless, fluctuating nothingness. Others suggest inflation was itself eternal, always happening somewhere, with our Big Bang just one moment in an endless churning sea of new beginnings. Those two ideas lead to very different pictures of what came before. And right now, the evidence cannot choose between them. The smoothness of the ancient light is real. The patterns in it are real. But the story inflation tells about the moments before the bang is still written in pencil, not ink. Researchers are refining their measurements, looking for faint signals called primordial gravitational waves, ripples in space itself that inflation may have left behind. If those signals are ever found, they might narrow the question. They might tell us something about the energy scale of inflation, about how violent or gentle that first expansion was. But they would still leave the deepest question open. What was there before the spring wound tight? Before the field, before the tension, before the moment everything began to rush outward. The universe keeps its smoothness and its silence. For most of human history, no one thought to ask what came before the beginning. Time felt like something that had always been there, stretching back without end, like a river with no source. The sky turned, the seasons changed, the stars rose and set. And most people assumed the universe had simply always existed, quiet and eternal, needing no explanation for its own origin. That assumption held for a very long time. The first serious cracks appeared not in a telescope, but in mathematics. In the early 20th century, a physicist named Albert Einstein completed a set of equations describing how gravity shapes space and time. He called it the general theory of relativity. When other scientists looked closely at those equations, they found something unexpected. The equations seemed to suggest that the universe was not static. It was either expanding or contracting. It could not simply sit still. Einstein himself did not like that answer. He added a term to his equations, a kind of mathematical counterweight, to force the universe to stay still. He called it the cosmological constant. He later described this as one of his greatest mistakes. Around the same time, an astronomer named Edwin Hubble was pointing telescopes at faint smudges of light in the night sky. Those smudges turned out to be entire galaxies, each one containing hundreds of billions of stars. And Hubble noticed something remarkable. The light from those galaxies was stretched. It had shifted toward the red end of the color spectrum, the way a sound stretches and deepens when its source moves away from you. The galaxies were moving away from us, not just a few of them, all of them in every direction. This was the first real observational evidence that the universe was expanding. If the universe is expanding now, then running it backward in time leads somewhere interesting. Run the film in reverse, and everything comes closer together. The galaxies converge. The distances shrink. The heat and density rise. Go back far enough, and all of space, all of matter, all of energy seems to compress into something unimaginably small and hot. That moment of extreme compression, that point where the backward-running film seems to end, is what we now call the Big Bang. A Belgian priest and physicist named Georges Lemaitre was one of the first to follow this logic carefully. He proposed in the 1920s that the universe had a beginning, a moment he described as the primeval atom. The idea was not immediately welcomed. Some scientists found it too close to a creation story. The name Big Bang was actually coined by a skeptic, the astronomer Fred Hoyle, who used it mockingly during a radio broadcast. He preferred a different model, one in which matter was continuously created and the universe had no beginning at all. That model, called the steady-state theory, had serious supporters for decades. The debate between these two views, a universe with a beginning versus a universe without one, was not settled by argument. It was settled by a discovery made almost by accident. In the mid-1960s, two radio engineers were trying to calibrate a large antenna in New Jersey. They kept picking up a faint, persistent hiss coming from every direction in the sky. They checked their equipment. They cleaned the antenna. They even removed a nest of pigeons that had taken up residence inside it. The hiss remained. It came from everywhere at once, equally strong in every direction, day and night, season after season. What they had found was the cosmic microwave background, a faint glow of ancient light left over from the early universe. It was the afterglow of the Big Bang itself, still traveling through space after billions of years. Its existence was a strong confirmation that the universe had once been extremely hot and dense. and had been expanding ever since. That discovery shifted the scientific consensus. The steady-state model faded. The Big Bang became the foundation of modern cosmology. But here is where the shape of time becomes complicated. The Big Bang tells us about the earliest moments we can observe. It does not tell us what, if anything, came before. The equations of general relativity, the same equations that predicted an expanding universe, break down completely at the moment of the bang itself. They produce infinities, values that have no physical meaning. The math stops working exactly where the question becomes most interesting. Some researchers believe this breakdown is a sign that general relativity is incomplete, that a deeper theory, one that combines gravity with quantum mechanics, is needed to describe what happened at the very beginning. Others wonder whether the question of before is even the right question to ask. The tools that revealed the Big Bang may not be the tools that can see past it. There is a strange idea that sits quietly at the edge of cosmology. It is the idea that the universe before our own might have left a mark, not a message, not a signal anyone sent on purpose, just a faint trace, the way a wave leaves a thin line of foam on a beach long after the water has pulled back. Some researchers believe that if a universe existed before the Big Bang, we might, in theory, be able to find its fingerprints. The surprising part is not that the idea exists. The surprising part is that some physicists think we may have already looked in the right place. We just cannot be sure what we are seeing. The cosmic microwave background is the oldest light we can detect. It is a faint glow that fills the entire sky, left over from roughly 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely for the first time. Scientists have mapped it in extraordinary detail. It looks almost perfectly smooth, with only the tiniest variations in temperature from one patch of sky to another. Those tiny variations became the seeds of galaxies. Most of what the background tells us fits neatly with what we expect from a hot, young, expanding universe. But some researchers have noticed something unexpected inside that map. There appear to be faint circular patterns, rings of slightly different temperature, scattered across the background sky. On their own, rings like that would not be remarkable. Noise and randomness can produce all kinds of shapes. The question is whether these particular rings are too regular, too consistent to be random. One hypothesis, put forward by the physicist Roger Penrose, is that these rings are echoes. Echoes of collisions between enormous black holes in a universe that existed before ours. In his model, called conformal cyclic cosmology, the universe passes through endless cycles. Each cycle ends and a new one begins. And the energy released by those ancient collisions, he proposes, might have left a ghostly imprint that survived the transition. This is where the counterintuitive part arrives. Most people assume the Big Bang erased everything that came before it. That seems logical. If all matter and energy and space were compressed into an almost impossibly small, hot point, surely nothing from before could survive. But Penrose's idea suggests that certain kinds of information, not matter, not energy in the ordinary sense, but something more like a geometric pattern, might pass through the transition in a way that ordinary physics would not. The rings, if they are real, would be the echo of that passage. Other researchers have looked at the same data and reached a different conclusion. They argue the rings are consistent with what random statistical noise would produce in a map that large and complex. The human eye is very good at finding patterns. The mind wants to see shapes. That tendency can lead even careful scientists toward patterns that are not truly there. The debate over whether these rings are real signals or statistical coincidence has not been settled. The evidence remains genuinely open. There is another surprise hiding nearby. Even if the rings are real, even if they do carry some trace of a prior universe, reading that trace is an entirely different problem. The cosmic microwave background is not a clean recording. It has been stretched, scattered, and distorted over billions of years. Foreground gas and dust in our own galaxy add noise. The instruments that measure it have their own limits. Pulling a faint signal from a previous cosmic cycle out of all, that interference would be like trying to hear a single whispered word from 1 billion years ago, spoken through walls and wind and time. Some researchers believe it may be possible with future telescopes. Others think the signal, if it ever existed, is simply too degraded to recover. What makes this genuinely strange is the scale of what is being proposed. Not just a signal from the distant past of our own universe, but a signal from before our universe existed at all. Before space as we know it, before time as we experience it. The idea that anything could carry information across that kind of boundary feels almost impossible to hold in the mind. And yet, the mathematics in certain models allows for it. Whether the mathematics describes something real, or whether it describes a beautiful structure with no physical counterpart, is exactly the kind of question that keeps cosmologists working late into the night. The echoes may be there. They may not. We may build instruments sensitive enough to know one way or the other. Or the answer may stay just beyond what any instrument can reach. For now, the sky holds its quiet, and the rings in the background glow on, meaning unknown. There is a question that sounds simple at first. It sounds like something a child might ask on a quiet evening, looking up at the stars. What came before the Big Bang? 4 words, a clean, easy sentence. And yet, the more carefully you sit with it, the more that question begins to fold in on itself, like a piece of paper you keep folding until it won't fold anymore. The problem is not that we lack good theories. We have several, and we've been visiting them gently throughout this long, slow night. The problem runs deeper than that. The problem is that the word before may not mean anything at all when we try to apply it to the beginning of everything. And that is not a dodge. That is not a way of avoiding the question. It is, some physicists believe, the most honest answer physics can offer right now. Here is why. Time, as best we understand it, is not a backdrop that was already there when the universe arrived. Time is part of the universe. It came with everything else. It is woven into the same fabric as space, as matter, as energy. When we ask what happened before the Big Bang, we are asking what happened before time existed. And that is a little like asking what is north of the North Pole. The question uses the right words. It follows the right grammar. But it points in a direction that may simply not exist. This idea connects to something physicists call the Hartle-Hawking no-boundary proposal, which we touched on earlier in this quiet night. The idea, put forward by two researchers working in the 1980s, suggests that time near the very beginning of the universe was not a straight line stretching backward into the past. Instead, it may have curved and closed in on itself, the way the surface of a sphere curves. On a sphere, you can travel in any direction and never reach an edge. There is no boundary. There is no outside. The Hartle-Hawking idea suggests the universe may be like that. There is no moment before the beginning, because the beginning itself is smooth and closed, with no edge to step past. But not everyone finds that satisfying. Some researchers feel that the no-boundary idea, while mathematically elegant, sidesteps the question rather than answering it. They argue that even a closed, smooth beginning still needs some kind of explanation. Why did that particular geometry exist? Why did anything exist at all? The no-boundary proposal tells us the shape of the beginning. It does not tell us why there was a beginning in the first place. This is where the question connects to something much older than physics. It connects to the deepest problem in philosophy. Why is there something rather than nothing? Physicists and philosophers have circled this question for centuries. Some believe science will eventually reach an answer. Others believe the question sits just outside the reach of any method we have, because every method we use, every equation, every observation, every experiment assumes that something already exists. We cannot use the tools of existence to explain existence itself. That loop may never close. And yet, the question keeps pulling at us. It connects the very large to the very small. It ties together general relativity, which describes how gravity shapes space and time on the grandest scales, with quantum mechanics, which describes how particles behave in the smallest places we can measure. These two great frameworks of physics do not agree with each other near the beginning. They produce different answers. They speak different mathematical languages. And until we find a theory that unites them, our picture of the very first moment will remain incomplete. Some researchers believe that a future theory of quantum gravity, a theory we do not yet have, might finally let us speak clearly about what before could mean, if it means anything. Others suspect that such a theory will simply confirm what the no-boundary idea already hints at, that the question dissolves when you look at it closely enough, the way a fog seems solid from a distance and then disappears as you walk into it. So the word before connects everything. It connects time to space. It connects physics to philosophy. It connects the universe we can see to the questions we may never be able to answer. It sits at the center of this whole long mystery, like a quiet knot, patient and still. We do not know if before is a real direction. We do not know if the question it asks has a real answer. For now, it is enough to notice how strange and beautiful it is that the question exists at all. For most of human history, people imagined the universe as something fixed, something permanent. The stars were where they had always been. The sky was the same sky. Change, if it came at all, came slowly and quietly, like seasons turning. Then, bit by bit, that picture began to shift. We learned that the universe is not fixed at all. It is expanding. The galaxies are drifting apart from one another, carried by the stretching of space itself. We learned that stars are born and die, that whole galaxies collide over billions of years, their shapes bending and folding into new forms. The universe is not a still painting. It is something in motion, always changing, always becoming something it was not before. And if the universe changes now, it is natural to wonder whether it was always changing, whether change itself goes back further than the Big Bang. One idea that tries to answer that question is called the Ekpyrotic theory. The name comes from an old Greek word meaning out of fire. It is a theory that imagines our universe not as a single isolated bubble, but as something more like a thin sheet floating in a larger space. To picture this, think of two enormous flat surfaces, almost impossibly large, drifting slowly toward each other through a dimension we cannot see or touch. These surfaces are called branes, short for membranes. The idea comes from a branch of physics called string theory, which suggests that the universe may have more dimensions than the three we move through every day. In the Ekpyrotic picture, our entire universe exists on one of these brains. Another brain floats nearby, just out of reach, separated from ours by a gap so thin it makes the width of an atom look vast. For an enormous stretch of time, these two brains drifted toward each other. Slowly, quietly, nothing dramatic happening yet. Then they touched. When the two brains collided, the energy from that collision flooded into our brain. It filled it with heat and light and matter. It set everything in motion. What we call the Big Bang in this picture was not a beginning at all. It was a collision, a meeting of two surfaces that had been drifting toward each other for longer than we have any way to measure. The Ekpyrotic theory was developed in the early 2000s by a small group of physicists who were looking for an alternative to the standard story of cosmic inflation. Inflation is the idea that the universe expanded extremely fast in its very first moments, smoothing out any irregularities and leaving behind the even, spread out cosmos we observe today. The Ekpyrotic model tries to explain that same smoothness in a different way, through the slow drift and eventual collision of brains, rather than a sudden burst of rapid expansion. One of the things the theory's supporters find appealing is that it does not require a beginning in the usual sense. Before the collision, both brains existed. Time existed, at least in some form. The question of what came before the Big Bang has an answer in this picture. There was a long, quiet period of drifting, a kind of cosmic patience, stretching across a dimension we have no way to observe directly. But the theory faces serious challenges. One is that it is very difficult to test. The brains themselves, if they exist, are beyond anything our instruments can reach. The extra dimensions required by string theory have never been directly detected. Some physicists find the whole framework too speculative to take seriously as a scientific theory. Because a theory that cannot be tested is hard to distinguish from a story, there is also a competing concern about what the collision would actually produce. Some researchers argue that the mathematics of a brain collision does not cleanly give rise to the kind of universe we observe. The details of how the collision generates matter and energy, and whether it produces the right patterns in the cosmic microwave background, the faint glow of ancient light left over from the early universe are still being worked out. The question of whether the Ekpyrotic model truly fits the evidence remains open. And even if the brains collided, even if that collision was our Big Bang, the question only moves one step back. Where did the brains come from? How long had they been drifting? What, if anything, existed before them? The universe keeps changing. Our ideas about it keep changing too. The Ekpyrotic theory is one of the newer shapes that the question has taken. A picture of fire born not from nothing, but from a slow and ancient meeting in the dark. Whether that picture is right, no one yet knows. There is a kind of light that never quite turns off. Imagine a candle that does not burn down. It just keeps going, casting its glow into the dark, long after everything around it has changed. Some researchers think the universe may work something like that. Not a single flame that lit once and faded, but something that keeps igniting over and over in corners of space we will never be able to see. This idea is called eternal inflation. It builds on something called cosmic inflation, which you may have heard mentioned in earlier sections of this long, quiet night. Inflation is the theory that the very early universe went through a period of incredibly fast expansion. Not fast the way a rocket is fast. Fast the way a single grain of sand might, in a fraction of a second, swell to the size of a galaxy. The universe stretched so quickly that the ordinary rules of physics could barely keep up. Most versions of inflation say this stretching eventually slowed down and stopped. The universe settled. Things cooled. Stars and galaxies began to form. But some researchers looked at the mathematics behind inflation and noticed something strange. The equations seemed to suggest that inflation, once started, might not stop everywhere at once. In some places, it would slow and settle, but in other places, it might keep going. This is the heart of the eternal inflation hypothesis. The idea is that inflation is not a single event that ended. It is an ongoing process, still happening right now, in regions of space so far beyond our reach that no light from them will ever reach us. Those regions keep stretching, keep expanding at rates we cannot observe. as they stretch, pockets of slower expansion form inside them, like bubbles rising in a glass of water. Each bubble settles into something like its own universe, its own space, its own time, its own physical laws, perhaps. Our universe, on this idea, is one of those bubbles. Think about what that means for the question we have been sitting with all night. If eternal inflation is correct, then there was no single moment of beginning. There was no clean edge where nothing became something. Instead, there was an ongoing process, stretching back through time, perhaps without any starting point at all. The light of our Big Bang was just one small flicker in a much larger, much older fire. But here is where the picture gets harder to hold. If those other bubble universes exist, we cannot see them. Light from beyond our cosmic horizon, the edge of the observable universe, can never reach us. The space between us and those other regions is expanding faster than light itself can travel across it. So the evidence for eternal inflation, if it exists, may be locked away in a place we can never look. Some researchers find this deeply unsatisfying. A theory that cannot be tested, they argue, is not really a scientific theory at all. It is closer to a story. A beautiful one, perhaps, but a story. Others push back on this and say that the mathematics of eternal inflation makes real, testable predictions about the patterns we see in our own universe. In the faint glow of the cosmic microwave background, the oldest light we can detect, if those patterns match what eternal inflation predicts, that is at least indirect evidence, even if we can never see the other bubbles directly. The debate remains open. It is one of the most honest debates in modern cosmology. There is something quietly beautiful about the image, though. Picture an endless dark sea. Across its surface, small lights appear, one by one. Each light is a universe, cooling and settling, forming its own stars, its own planets, its own long, slow history. The sea itself never stops moving. It churns and stretches in the dark between those lights, always expanding, always generating new pockets of calm. Our light, the one we live inside, is one small glow among perhaps an uncountable number. We do not know if this is true. We may never know. The light from those other regions will never reach us, and the darkness between us and them is growing wider every moment. But the mathematics that points toward this picture comes from the same equations that have correctly described so much of what we can observe. That is not proof, but it is something worth sitting with quietly. The universe may not have had a beginning the way a story has a first sentence. It may be more like a fire that was already burning when our small corner of it first caught the light. There is a word in physics that sounds almost ordinary: entropy. It means, in the simplest terms, the tendency of things to spread out, to scatter, to move from order toward disorder. A drop of ink in a glass of water does not gather itself back into a drop. Heat does not flow from a cold stone into a warm fire. Things spread. Things mix. Things do not, on their own, return to where they started. That spreading, that slow drift toward disorder, is entropy at work. And entropy, some researchers believe, may carry a kind of memory. Not memory the way a mind holds a thought. Something quieter than that. A physical record written into the structure of the universe itself, of how ordered or disordered things once were. If that idea holds, then the state of the universe today, its particular arrangement of matter and energy and heat, might tell us something about what came before the Big Bang. Not everything, not clearly, but something. The question begins with a puzzle that has bothered physicists for a long time. The universe we can observe began in an extraordinarily ordered state. The matter was smooth, almost perfectly even, spread across space with only the tiniest variations. That smoothness is strange. Disorder is far more common than order. If you imagine all the possible ways a universe could begin, the vast majority of those ways would be chaotic, lumpy, irregular. A smooth beginning is, in the language of physics, deeply unlikely. So why did our universe start so ordered? One possibility is that it simply did. That the low entropy beginning was a random event, a cosmic accident with no cause we can trace. Some theorists accept this and move on. The universe started ordered. We live in it. That may be all there is to say, but others find that answer unsatisfying. They wonder whether the smooth beginning of our universe was shaped by something that came before. Whether whatever existed before the Big Bang was itself in a particular state, and whether that prior state left its mark on ours. Roger Penrose, a British mathematician and physicist, has spent decades thinking about this. His idea, called conformal cyclic cosmology, suggests that our universe is one in a long chain of universes, each one beginning where the last one ended. In his model, the far future of a dying universe, a cold, dark, nearly empty place, is mathematically similar to the smooth, hot, dense beginning of a new one. Entropy in this picture does not simply increase forever. It resets. The end of one universe becomes the low entropy starting point of the next. Penrose has even suggested that faint signals from the previous universe might survive into ours. He calls them Hawking points, named for his longtime colleague. They would appear as subtle circular patterns in the oldest light we can detect, the cosmic microwave background. Some researchers have looked for these patterns and believe they have found hints of them. Others have looked at the same data and concluded the patterns are not there, or that they are no more than what random chance would produce. The evidence, as of now, remains genuinely contested. A different approach comes from the study of thermodynamics, the science of heat and energy, and the direction time flows. Some physicists argue that time itself flows in one direction because entropy increases in that direction. The past is the direction of lower entropy. The future is the direction of higher entropy. If that is true, then asking what came before the Big Bang is really asking what came before the lowest entropy state we can identify. And some theorists wonder whether that question has an answer at all, or whether the concept of entropy simply breaks down at the moment of the bang, where our usual rules stop working. There is also a quieter possibility. Some researchers suggest that the low entropy of our universe's beginning was not shaped by anything that came before. Instead, it may be a selection effect. In a vast collection of possible universes, only those with smooth, ordered beginnings produce the kind of stable stars and planets and conditions where anyone could be around to ask the question. we find ourselves in a low entropy universe because only low entropy universes produce observers. This idea, sometimes called the anthropic argument, does not tell us whether a previous universe existed. It only tells us why we would find ourselves in this particular one. What entropy remembers, then, is uncertain. It may remember a previous universe. It may remember only the particular accident of our own beginning. It may not remember anything at all, in any meaningful sense. The record, if there is one, is written in a language physicists are still learning to read. There is something quietly beautiful about the way mathematics works. You write down a few symbols on a page. You follow the rules. And somehow, the numbers lead you somewhere you never expected to go. That is what happened when some researchers began thinking carefully about black holes. They were not looking for a theory of creation. They were just following the math. And the math, in its patient and unhurried way, suggested something extraordinary. A black hole is a place where gravity has become so strong that nothing can escape it. Not light, not time, not information, as far as we can tell. At the center of a black hole, the equations of general relativity, the set of rules that describes how gravity shapes space, reach a point called a singularity. A singularity is where the numbers stop making sense. Density becomes infinite. Volume becomes zero. The equations break down completely, like a calculator asked to divide by nothing. That breakdown is familiar. It is the same kind of breakdown that appears at the very beginning of the Big Bang. In both places, the math hits a wall, and some researchers began to wonder whether that wall might be a door. One idea developed over decades, and still very much an open question, is that the interior of a black hole might give rise to an entirely new universe. The physicist Lee Smolin explored this possibility in what he called cosmological natural selection. The idea is careful and strange in equal measure. When matter collapses into a black hole and reaches that central singularity, the conditions there may be similar to the conditions that existed just before our own Big Bang. Extreme density, extreme heat, a kind of cosmic pressure so vast it defies ordinary description. One possibility is that those conditions could trigger a bounce, a new expansion hidden inside the black hole, invisible to anyone outside it. If that is true, then our universe may have been born inside a black hole that formed in some earlier universe. And every black hole in our universe may be seeding a new universe of its own right now, in some dimension we cannot reach or observe. The mathematics behind this idea draws on the same equations that describe the Big Bang. The numbers are not invented. They follow from real physics. But whether they describe something real, whether a new universe truly blooms inside a collapsing star, remains entirely unknown. The theory cannot be tested from the outside. A universe born inside a black hole would be causally sealed off. No signal could cross that boundary. No measurement could confirm it. The math points toward a possibility. It cannot yet point toward a proof. Smolin's version of the idea goes further still. He suggested that each new universe might inherit slightly different physical constants from its parent. Constants are the fixed numbers that govern how physics works. Things like the strength of gravity or the mass of an electron. In our universe, these numbers have very precise values. Change them even slightly, and stars cannot form. Change them more, and atoms themselves fall apart. Smolin wondered whether universes that produce more black holes might pass on their constants more often, like a kind of cosmic inheritance. Over vast stretches of time and generation after generation of universes, the constants that favor complexity might become more common. It is a beautiful idea. It borrows the logic of natural selection and applies it to the cosmos itself. But it is also deeply contested. Other researchers point out that we have no way to observe other universes, no way to test whether constants vary across generations, and no way to confirm that black holes produce anything at all beyond their own crushing gravity. The elegance of the mathematics does not guarantee that the picture is correct. What the mathematics does guarantee is that something strange happens at a singularity. The equations reach their limit. And when equations reach their limit, that is often a sign that a deeper theory is waiting to be found. Quantum gravity, the still unfinished attempt to unite the very large with the very small, one day replace the singularity with something more manageable, something that does not break, something that continues. What that continuation looks like, no one yet knows. Whether it produces a new universe or simply a different phase of the same one, or something the human mind has not yet imagined. The question stays open. The numbers lead us to the edge. They do not yet tell us what lies beyond it, but they keep pointing. Quietly, patiently, in the language of mathematics, they keep pointing towards something just out of reach. There is something quiet and strange about the way time moves. It only goes one direction. You can stir cream into coffee, but you cannot unstir it. You can watch a glass fall and shatter, but you will never watch the pieces leap back up and reassemble. Something about the universe seems to insist on this. And yet, when physicists look at the fundamental equations that describe how particles move and interact, those equations work just as well running backward as forward. The math does not care which way time flows. So, why does everything else seem to? This is the puzzle of the arrow of time. It is one of the deepest open questions in all of physics, and it connects, in a quiet but important way, to the question of what came before the Big Bang. The arrow of time is tied to something called entropy. Entropy is a measure of disorder, of how many ways the pieces of a system can be arranged. A tidy room has low entropy. A messy one has high entropy. There are far more ways to be messy than to be tidy, so things tend to drift toward disorder over time. This tendency is called the second law of thermodynamics, and it is one of the most reliable patterns in all of science. Entropy, as far as we can tell, almost always increases. That increase is what gives time its direction. The past is the state of lower disorder. The future is the state of higher disorder. But here is where the mystery deepens. If entropy always increases, that means the universe must have started in a state of very low entropy. Extraordinarily low, in fact. The early universe, in the moments after the Big Bang, was arranged in a way that was almost impossibly orderly, at least in terms of its energy distribution. Some physicists find this deeply puzzling. Why would the universe begin in such a precise, low entropy state? there is no obvious physical law that demands it. It seems, in some sense, like a very specific and fragile starting condition. One possibility is that the low entropy of the early universe is simply a feature of whatever process created it. If the Big Bang emerged from a quantum event or from a previous collapsing universe, or from a fluctuation in some larger structure, then perhaps that process naturally produced a low entropy beginning. But this only pushes the question back further. Where did that prior low entropy state come from? The problem does not disappear. It retreats. Some researchers wonder whether the arrow of time might not be as universal as it seems. In a universe vast enough or old enough, there may be regions where entropy decreases locally, where things briefly become more ordered before dissolving again. These would be rare and temporary. But the possibility raises a strange thought. If time's direction is tied to entropy, and entropy is not absolutely fixed in its behavior, then perhaps time's arrow is not a fundamental feature of reality. Perhaps it is something that emerges from conditions rather than something built into the fabric of existence. Roger Penrose, the physicist whose conformal cyclic cosmology appeared in an earlier part of this exploration, has thought carefully about entropy and the beginning of time. His model suggests that the universe passes through vast cycles, each one ending in a state of maximum entropy before somehow resetting into a new low entropy beginning. In his view, the arrow of time is not erased between cycles. It is, in some deep sense, continuous. But how that reset happens, and what it means for the nature of time itself, remains an open question even within his framework. Other researchers take a different view. They suggest that the arrow of time might be a kind of illusion produced by the scale at which we observe things. At the level of individual particles, time may be symmetric. At the level of galaxies and coffee cups and human lives, the asymmetry emerges from statistics, from the sheer number of particles involved and the overwhelming probability of disorder increasing. On this view, time's direction is real but not fundamental. It is something that appears when you zoom out far enough. What all of these ideas share is a sense of fragility. The arrow of time, the direction, in which everything flows depends on a starting condition that no one fully understands. Change that starting condition, and time might behave differently. Or it might not exist in the way we experience it at all. The universe we live in, with its past and its future, and its one-way drift toward disorder, rests on something that physics has not yet fully explained. The equations allow for other possibilities. Why this one was chosen, or whether it was chosen at all, remains quietly, beautifully unresolved. There is a kind of silence that light cannot cross. We have sent our instruments deep into the sky. We have built telescopes that gather the faintest whispers of ancient radiation. We have mapped the oldest light we can detect, that soft glow left over from the early universe, and we have learned a great deal from it. But there is a wall, not a wall we can see or touch, a wall built from the nature of light itself and from the nature of what came before it. For the first few 100,000 years after the Big Bang, the universe was too hot and too dense for light to travel freely. Everything was a thick, bright fog. Photons, the tiny particles that carry light, could not move more than a short distance before being absorbed and scattered again. The universe was opaque, the way a cloud is opaque. You can see the cloud glowing, but you cannot see through it to whatever is on the other side. Then, slowly, things cooled. The fog lifted. Light broke free and streamed outward in every direction. That moment is called recombination. The point when electrons settled into atoms and the universe became transparent for the first time. The light from that moment is what we call the cosmic microwave background. That faint, ancient glow that fills the whole sky. It is the oldest light we will ever see, and it is still not old enough. Everything that happened before recombination is hidden from us, at least from the perspective of light. The first seconds of the universe, the first fractions of a second, the moment of the bang itself, none of that left light we can observe directly. The fog erased the view. So when we ask what came before the Big Bang, we are asking about something that even our best telescopes cannot reach. We are asking about a time before light could speak. Some researchers believe there may be other messengers. Gravitational waves, ripples in the fabric of space itself are not blocked the way light is. They pass through matter almost without noticing it. If the very early universe produced gravitational waves, those waves might still be moving through space right now, carrying information from moments we cannot see with any camera or mirror. Detecting them would require instruments of extraordinary sensitivity, far beyond what we currently have. It is a possibility, not a certainty. And even if we detected them, reading their message clearly would be a separate challenge entirely. Neutrinos offer another faint hope. These are nearly massless particles that barely interact with anything. They, too, could in principle carry signals from the earliest moments of the universe. A neutrino background from the first seconds after the bang may exist, spread thin across the cosmos. But detecting it would require technology we have not yet built, and the signals would be vanishingly faint. Whether we could ever read them clearly enough to learn something about what came before remains an open question. There is also the deeper problem. Even if we gathered every gravitational wave, every ancient neutrino, every possible signal the early universe could have sent, we would still be looking at things that happened after the bang itself, and whatever preceded it may have left no signal at all that can survive into our universe. Some models suggest that any information from a previous epoch, a previous universe, a previous state of existence would be scrambled beyond recovery by the violence of the bang. The slate, in this view, was wiped clean. Other models disagree. Penrose's conformal cyclic cosmology, for instance, suggests that certain patterns from a previous cosmic age might survive, faint and distorted, in the structure of the microwave background. Some researchers have looked for these patterns and reported hints. Others have looked at the same data and found nothing convincing. The debate is ongoing, and the evidence is not yet clear enough to settle the question. What we are left with is a boundary, a horizon, not the edge of space, but the edge of what light can tell us. Beyond it, the universe keeps its oldest secrets in a language we have not yet learned to read and may never learn. That is not a failure of science. It is simply the shape of the problem. The universe is not obligated to make itself legible to us. And yet, the search continues. New instruments are being designed. New methods are being imagined. The boundary feels fixed, but the history of science is full of boundaries that turned out to be more permeable than anyone expected. Whether this one will yield, no one can say. For now, the oldest light we have is enough to fill a quiet night with wonder. There is a faint glow that fills the entire sky. You cannot see it with your eyes. It sits below the range of visible light, humming quietly in the microwave part of the spectrum. It is called the cosmic microwave background, and it is the oldest light we can detect. It was released roughly 380,000 years after the Big Bang, when the universe cooled just enough for atoms to form and light to travel freely for the first time. Before that moment, the universe was too dense and too hot for light to move at all. What we see in this ancient glow is a kind of baby picture of the cosmos. But some researchers wonder if that picture contains something older still. Something that might have survived from before the Big Bang itself. The cosmic microwave background is not perfectly smooth. It has tiny variations, small patches that are slightly warmer or cooler than average. These variations are measured in millionths of a degree. They are so slight that they are almost nothing at all. And yet, they carry enormous information. They are the seeds from which galaxies eventually grew. The pattern of those variations matches very well with what the theory of cosmic inflation predicts. Inflation, the idea that the universe expanded at an extraordinary rate in its very first moments, would have stretched tiny quantum fluctuations into the large-scale patterns we observe today. So the map of the microwave background is already a kind of fossil record. It preserves the shape of the very early universe in a way nothing else can. The question some researchers are now asking is whether it might also preserve something from even earlier than that. One idea comes from a physicist named Roger Penrose. His model, called conformal cyclic cosmology, suggests that our universe is just one in a long chain of universes. Each universe expands, cools, and eventually ends in a state of maximum disorder. But Penrose proposes that this ending is, in a strange mathematical sense, identical to a new beginning. One universe's far future becomes the seed of the next universe's Big Bang. If this idea is correct, then the previous universe might have left faint marks in our microwave background. Penrose and his colleagues have reported finding what they call Hawking points in the data, circular patterns of slightly different temperature that they believe could be the echoes of supermassive black holes from a universe before ours. Other researchers are not convinced. They have looked at the same data and concluded that these circular patterns are consistent with random noise. The statistical case, they say, is not strong enough to claim a real signal. The debate is ongoing, and the question remains genuinely open. A separate line of inquiry comes from loop quantum cosmology, the model that replaces the Big Bang with a big bounce. In this picture, a previous universe collapsed inward and then rebounded into our own. Some researchers working within this framework have proposed that the bounce might have left a specific kind of imprint in the microwave background, a faint signature in the way light is polarized, meaning the way its waves are oriented as they travel. Detecting that signature would require instruments more sensitive than anything we currently have. But future telescopes and space-based detectors may be able to look for exactly this kind of signal. This is where the future of the question lives. Not in grand philosophical arguments alone, but in the careful, patient work of measuring the sky with ever greater precision. New observatories are being planned and built. Some will focus on the polarization of the microwave background in extraordinary detail. Others will search for gravitational waves, ripples in space itself, that might carry information from the universe's earliest moments, or perhaps from before them. The challenge is that even the best data may not be enough. The microwave background only reaches back to 380,000 years after the Big Bang. What happened before that is hidden behind a wall of hot plasma that light could not cross. Gravitational waves, if they can be detected from that era, might pierce that wall. But whether any signal from before the Big Bang could survive the violence of the bang itself is something no one yet knows. The universe keeps its oldest secrets well. The microwave background glows on, patient and ancient, carrying its faint patterns across billions of years. Whether those patterns contain a whisper from a universe that came before ours is a question that future instruments might one day answer, or they might only deepen the mystery. For now, the glow is there, soft and constant, filling the sky in every direction, waiting to be understood. There is a question that has been sitting quietly at the center of this whole conversation. Not just the question of what came before the Big Bang. Something a little deeper than that. Something that asks whether the question itself is one that physics can ever honestly answer. It sounds strange at first. Questions are just questions. You ask them, and eventually, with enough time and enough clever thinking, you find the answer. That is how science works. That is how we mapped the stars and measured the age of the universe and traced the faint glow of the cosmic microwave background all the way back to the first few 100,000 years after everything began. But this question is different. And the reason it is different has to do with something very simple. Time. When we ask what came before the Big Bang, we are using the word before, as though time were already there, waiting, like an empty stage. We imagine a long corridor of moments stretching backward, and we wonder what was standing at the far end. But some physicists suggest that time itself may have begun at the Big Bang. Not just the universe, not just matter and energy, time itself. If that is true, then asking what came before the Big Bang is a little like asking what is south of the South Pole. The question uses the right words. It sounds like a real question, but the geography does not allow for an answer. There is no south beyond the southernmost point. There may be no before beyond the first moment. This idea comes partly from the Hartle-Hawking no-boundary proposal, a theory developed by two physicists that imagines the beginning of the universe the way you might imagine the surface of a sphere. A sphere has no edge. You can walk across it in any direction and never fall off. In this model, the universe has no beginning in the way we usually picture a beginning. It simply curves back on itself. The question of what came before dissolves, not because someone answered it, but because the shape of the answer leaves no room for the question. Other researchers push back on this, They argue that time did not simply begin. They point to models like loop quantum cosmology, which suggests that time stretched backward through a collapse, through a bounce, into a previous universe that existed before our own. In that picture, before is a real direction. The question is not meaningless. It is just very hard to answer. And that disagreement is itself remarkable. Two serious, careful ways of thinking about the universe, and they cannot even agree on whether the question makes sense. One says the question dissolves. The other says the question is real, but may be unanswerable with the tools we have. Both of those possibilities are worth sitting with. Here is what makes this feel personal, even from this distance. The atoms in your body are old. The calcium in your bones was forged inside stars that burned and collapsed long before our sun existed. The iron in your blood came from those same stellar furnaces. You are, in a very literal sense, made of the universe looking at itself. And the universe you are made of traces its history back to a single moment that we cannot see past. That moment is the edge of everything we know, and the question of what lies beyond it, or whether beyond even means anything there, is one of the deepest questions a human mind can hold. Some philosophers argue that the question is not just scientifically difficult. It may be structurally outside the reach of any science built on cause and effect. Science works by tracing causes backward. But if time had a beginning, there is no backward to trace. The chain of causes stops, and we are left not with an answer, but with a kind of open space where an answer might have been. Others find that unsatisfying. They want the chain to continue. They want there to be something on the other side. And so the theories keep coming. The bouncing universe, the colliding membranes, the eternal inflation that never quite ends. Each one is a way of saying, the question is real, and we are not done asking it. Both impulses are deeply human. The desire to accept the limit, the desire to push past it. You are made of the same material as everything that has ever existed in this universe. The question of where it all came from lives inside you in some quiet way, whether you think about it or not. Tonight, you have thought about it, and the question remains open, patient, and vast. way the sky is vast when you look up at it on a clear and silent night. We have come a long way tonight. We started at the edge of everything we can see, standing at the rim of the observable universe, looking back toward a moment so distant and so strange that our best tools can barely reach it. We asked a question that has no clean answer. We asked what came before the Big Bang, and we sat with that question, turning it slowly, the way you might turn a smooth stone in your hand on a quiet evening. We found that some theories say there was no before. Time itself may have begun with the universe, the way the surface of a sphere has no edge. You can walk in any direction and never fall off. There is simply no place called before to point to. The Hartle-Hawking idea asks us to accept that time, like space, may have a shape that simply closes on itself. The question dissolves before it can be answered. Other theories say something was there. A previous universe, contracting slowly until it reached a single dense point, then bouncing outward into what we call the Big Bang. The loop quantum cosmology picture imagines a kind of cosmic breath, an inhale and an exhale, one universe giving rise to the next. There is no first breath in that picture. There may never have been one. Still others imagine vast, thin membranes floating in a higher dimensional space, drifting for unimaginable stretches of time before brushing against each other and releasing a burst of energy that became our universe. In that picture, the collision was not a beginning. It was more like a spark from two stones that had been waiting a very long time. And then there is the idea that our universe is just one bubble in an endless, churning sea of universes, each one born from the same restless quantum energy, each one expanding into its own private space. In that picture, there was never a true beginning. There was only the slow, endless production of new beginnings, one after another, stretching back without a start. None of these ideas has won. None of them has been proven. The evidence we have, the faint glow of the cosmic microwave background, the way galaxies are spread across the sky, the tiny ripples in the oldest light we can detect, all of it is consistent with more than one of these pictures. The universe has not told us which story is true. It may never tell us. The physics we have today breaks down at the very moment we need it most, right at the beginning, where the temperatures and densities exceed anything our equations can handle cleanly. So we are left with open hands. And there is something peaceful in that. The universe does not owe us an answer. It simply is, vast and old, and quietly going about its work, spinning galaxies into shape, pulling clouds of gas into stars, letting those stars burn for millions of years before they scatter their elements into the dark. Somewhere in that dark, a small blue planet turns slowly, its oceans catching the light of a moon that has been keeping it company for billions of years. Right now, that planet is turning. The side you are on has tilted away from the sun, and the sky above you has gone dark and full of stars. Those stars are so far away that their light left them years ago, some of them thousands of years ago, and it has been traveling quietly through empty space ever since, just to reach your sky tonight. You are resting beneath all of that, beneath the stars, beneath the question of what came before them, beneath the theories and the mathematics and the beautiful uncertainty of it all. The universe holds you the way it holds everything, without effort, without preference, without asking anything in return. The question of what came before the Big Bang may be answered someday, perhaps by a new kind of telescope, perhaps by a new kind of mathematics, perhaps by an idea that no one has had yet, or it may remain open, a permanent horizon at the edge of what any mind can reach. Both possibilities are, in their own way, astonishing. For now, the question can rest. You can rest with it. Let it float somewhere at the back of your mind, soft and unresolved, like a light you can see but cannot quite name. The universe is old and wide, and full of things we do not yet understand. And tonight, that is enough. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.